Okay, next we talk about Seaborn. That's a very high level plotting library built on top of Matplotlib. So one thing that you must notice, or you must know, that all the visualizations that you can achieve in Seaborn, they are achievable in Matplotlib as well. But several times, due to really high level interface of the Seaborn, you can achieve certain kind of plots, certain kind of visualizations much easier in Seaborn as compared to Matplotlib. Although you can do the same stuff in Matplotlib, Seaborn itself is built on top of Matplotlib, so Seaborn is not going to give you a functionality that is beyond the reach of Matplotlib, but it is going to give you an interface that in certain kind of plots, it will be much easier to use Seaborn rather than Matplotlib. Further, this Matplotlib and Seaborn, they can be used in combination, that we will see shortly, to achieve very beautiful kind of visualizations. One another thing, that SNS, or this Seaborn imported as SNS alias, it actually gives the layouts, the axis layouts that are very beautiful and much more appealing and engaging as compared to the default or the available axis styles and in Matplotlib. Although Matplotlib recently is also increasing its styles to follow these kind of styles in Seaborn, but Seaborn has really cool kind of these styles, default styles. So let's say let's start with just a simple comparison of this Matplotlib and Seaborn. First of all, let's import Seaborn as SNS. Let's import that. So that's imported. So plt dot style, let's say dot use. Let's use a classic style just to give you a look and feel of difference between the style of this Matplotlib and Seaborn. So let's generate some data just for a simple plot. Let's say np.linspace. Let's start from 0, end at 100, and let's generate maybe 1,000 points. Yeah, so that's x. Let's say y is simply, let's say, cumulative sum of, again, the random numbers, random dot rand n, and let's say these are 1,000 by 5. So let's say these are 1,000 by 5. So these are basically five vectors. Let me just show you the shape of y. It is basically 1,000 by 5, and x is just if you see the shape of x, sorry, I should write that, x dot shape, that is basically 1,000. Now you have x and you have y. Y are actually, you have 5 outputs against x, just we have generated randomly. Let's use plt dot plot simply x and y, and let's use the legends. Let's say legend. What kind of legend we really, let's say the legends are A, B, C, D, and E. Let's say these are the legends. How many columns you want the legend to spread on? Let's say 2. And what should be the location of your legend? Let's say the location of legend is upper left corner. So if you see that, you will see this kind of plot. Let me scale it properly so that you can see the whole plot. That's the plot with classic layout. Let us just change simply the layout and keep everything else the same. Let's just simply change the layout. We are going to use the layout from Seaborn, the default layout, and we will see how the plot looks like just with that. So let's say so let's set the layout. For example, sns.set, it will set a layout from Seaborn. There are several layouts, but I'm setting a default one. And now you will be seeing the plot just because of the layout. It looks like much more engaging than the plot you have just seen on the above. Again, I'm not saying that this kind of layout is not available in Matplotlib or you cannot achieve that. You can do all that stuff, but Seaborn actually gives you kind of one-liners to achieve these kind of cool and engaging plots. Not only that, I mean, you have cool functions for displaying, for example, densities and histograms and all that stuff. So, for example, um, let's just display certain histograms in Matplotlib first. Although we have set the layout, and then we will see how to actually display the density plots using SNS KDE plot function. So let's just go through with um, some of the histogram plots in Matplotlib. So let's generate X is, let's say, np dot random dot rand n. Let's say, let's generate 5,000 points. Yeah, and let's say all these points has standard deviation not 1 but somewhere with a factor of 50. Let's say y is let's say 200 np dot random dot rand n. Let's say these are also 5,000 points, and let's have a z as well with again the variance or the standard deviation smaller than y. Random dot rand n, and let's say these are also 5,000 points, and let's say this particular z is not centered at origin, but it rather is shifted 500 units to the right. Now let's say plt.hist, let's say x, where density is true. If you do not set this density true, the histograms, they will not be up to a scale, and one histogram may dominate the other in the scale. So it's always good to display the density to keep the scale and the area under curve as 1. So alpha is 0.5, let's say, just to build the opacity. So next we can have this plot for y and the plot for z. So we can have a plot for y as well, and we can have a plot for z as well. So let's say now if you see that these are the density plots. Let me just zoom in. So you can see now these are the density plots available by Matplotlib. We can have the density plots, for example. We can have the density plots, for example, using these are the histogram plots. Also, we can have the density plots, the curves that actually approximate the probability distribution of all these. And let's use a density function from Seaborn library, which is the KDE plot. Let me first build a data frame out of these 3 columns that we just have right now. Let's say data is pd dot data frame. Have we imported pandas earlier? Yeah, no. I guess we have. So we should have import. Even if you have not, we should import that now. Import pandas as pd. Let's say data equals pd dot data frame, pd dot data frame, and let's say we have data frame with x, or maybe okay, the name is x and the value is x. The second column is y, and its column entries are in y. The third column is z, and its values are in z. You can have these different names. For example, you can have this a, b. You need not to have the same kind of names, and then c maybe. Yeah, that's your data. Once the data frame is generated, what you can do is, for example, you can iterate over the columns of the data in data.columns, and you can have plt.hist as before, but now you will be iterating over for each column of the data, and maybe you want a density plot. The area under curve must be 1, and maybe you use some alpha blending with 0.5 maybe. And on top of that, you can have, for example, this KDE plot. The KDE plot basically is kernel density estimate plot. That's a continuous approximation of probability function that can be approximated from the data. There are a lot of ways to calculate the densities. One way is to use the kernel density estimate. There are others as well. So let's see how the plot looks like. Oh, there is some error. What error? Yeah, there is some error. A rectangle object has no property alpha. Okay, so misspelling again. I guess I have spelled everything. I messed up with spelling. A-L-P-H-A, alpha. Yeah. So that's alpha. Now let's run that code, and we can have this plot that looks extremely cool. Let me set the zoom level so that you can. So the histograms as earlier as before, but these density plots or the continuous curves, they're actually showing the continuous distribution function for each of the columns individually. I should mention here that you can have these kind of plots directly from the data frame. There are ways to plot directly the pandas object, the columns, but that we will be discussing in our actually comprehensive course related to this data understanding and visualization. Here in this particular tutorial, I'm just going to talk about the matplotlib, Seaborn, and Bouquet. But these kind of plots, they can be achievable directly from the pandas data frame as well. So now if you see the kernel density plot, that is much cooler than earlier. And this is not, by the way, this is not the only way to plot these kernel densities. You can have, for example, this Seaborn actually gives you further functions to plot these densities in more fine-grained form. For example, there's another function called dist plot. So let me go for that for column in data.columns, and let's say sns.dist plot, distribution plot for each data column. And here you need not to specify anything. Just do that, and if I just show you that plot, that is much cool and nicer than you have seen earlier. Here, for example, these are the distribution plots. So you can use KDE. You can see the difference between KDE, and you can use the dist plot for distribution SNS. Yeah, so moving forward, we can have, for example, we can have joint plots as well, where you want to see the joint distribution of two different columns or variables in a particular data frame. And not only the joint distribution, you may want to see the individual distributions on top. And let's see what I'm talking about. Let's change the SNS axis style to, let's say, white. That's a cool style for what I'm going to do, just for that. And we can have SNS joint plot, and joint plot has, let's say, the variables A and the variables, let's say, B. These are the two variables I'm talking about this data, and what kind of plot I'm really interested in. On top of the x's, I want the density estimates on top of the x's. So it may take a while to complete. So if you see here, that's a much cooler plot. Let me just show you that in a proper scale level. So that's the axis A. That's the axis A. Let me show you that. This is axis A and this is axis B. So this is all the data in column A. The distribution of the column A, the kernel density of column A is there. The distribution of column B is there, and the joint distribution basically is here. So the darker the color, the more distribution inside. The fairer the color, the distribution is vague outside or just, I mean, in the center you can see here, the peak is in the center. That means the color is darker. As you move away, these are kind of contours. If you move away from the center, the distribution just falls down, and that's what it looks like. Not only A and B, you can have, for example, between C and B, you can have that distribution as well. So whatever pair of data points you just want to see. Here you can see the plot looks like a little different. In C you have, for example, this is the range from 0 to 900, and the density is again normal. Here for B, the density is normal, and again the same stuff. So yeah, so that's, and you can further place legends there and place labels there, and you can annotate this a lot the way you really want to do that. Next we talk about one more very powerful feature of this Seaborn library, which is pair plot. There are so many powerful functions in Seaborn library, but this one is really cool. I mean, this pair plot function. So before actually introducing this pair plot, let me just load some classification data just to show you the power of this pair plot. So let's load this iris data that is available in SNS dataset. So iris, the dataset is also available in scikit-learn.dataset module or packages, that is also available there. So that's our dataset. Let's see if the dataset is loaded properly or not. Yes, it is loaded. So iris.head, for example, let's see, 60 values, and these are all the 60 values. So it has 4 features: sepal length, sepal width, petal length, petal width, and species, and all that kind of. And obviously we have for different classes, the different kind of classes are these species. So let me for example give you iris dot species dot unique values. So it should give me the unique values. The classes are Setosa, versicular, and virginica, and the total number of data points here are iris dot shape. For example, if you see, so there are 150 data points, each with the 4 features, and the 5th value or the 5th column basically represents the class label. That's a classification data. We can also see the columns here, and the columns basically are sepal length, that's a feature; sepal width, that's a feature; petal length, that's a feature; petal width, that's a feature, and so on. What if we want to see the distribution of sepal length and sepal width? What do we want to see? The scatter plot of sepal length and sepal width together. And not only that, we want to see that distribution with respect to each species. So for example, for each kind of class, there are 3 classes here: Setosa, versicular, and virginica. With reference to each class, I want to see the distribution or the scatter plot of let's say sepal length and sepal width. Not only this pair, I want to see the distribution or the relationship, basically the dependency, visual relationship between sepal length and petal length. I also want to see the relationship between sepal length and petal width. Maybe I want to see the correlations between different features. And what if I want to do that for every pair possible? And for every pair possible with respect to each class, how can I do that? Well, I can write a code here and we can do that stuff. But here is what is available from SNS. Just a simple command: sns.pair plot Seaborn. So pair plot, and we just give iris, and then we specify what is the class, what is the feature that what is the column that should be used as a class label, just to separate different colors together. And if you now run this, you'll be see extremely cool plot here. Yeah, so let me show you that plot by just scaling it properly. So yeah, so here you can see, for example, this first of all, you see that the three different classes, they are given different colors. So blue is for setosa, orange is for versicolor, and virginica just got the green color. You can just see here the sepal length and the petal width, they both have this kind of relationship with respect to each class, which means if you just use these two features rather than all, you may get very good distinction. Here, sepal length, for example, this column is all the sepal length with all the other features. For example, sepal length with petal length, sepal length with sepal width. Here you can see sepal length with sepal width actually mixes virginica and versicolor together. I mean, the two features, if used just alone, may confuse the two classes if you use just these two features for classification. On the other hand, if you see, for example, here in this particular plot, if you see the petal length and the petal width, they actually separate the two classes very beautifully. Also, you have on the same kind of diagonal, you have kernel density estimates or the kernel density plots for each particular class individually. Yeah, so I mean, this is really powerful feature. The same kind of feature is available also in Panda's plotting library called the scatter matrix. Yes, we should also know the Seaborn function for that, because it is just one-liner and extremely powerful to basically achieve a lot of cool stuff like pair plots. And even if you have, for example, I mean, hundreds and hundreds of features, it will be able to plot all of them, the pairs of all of them. How cool is that? Yeah. So next we talk about, let's say, some 3D plots that are available. Although I can talk more about this Seaborn, and we actually have very comprehensive discussion in our full course. Let me switch now towards some 3D plottings, three-dimensional plot. What really a three-dimensional plot is when you have, for example, the variables when you have, for example, two variables. Let's say this is x, this variable is x, and let's say this variable is y. This may be some feature, maybe let's say sepal length in iris data maybe, and this may be another feature, maybe petal length in iris data, and you may want to be interested in some value that is a function of x and y. So for example, let's say the z value is simply x plus 2y, or maybe x squared plus 2y. In that case, if I supply the x value as 0, for example, and y value as 4, let's say, then what will be the z value? The z value will be 0 squared plus 2 times 4, and z value will be 8 at that particular location. Z value will be 8. Similarly, I can go through the whole this grid. For example, 0 with 4, 0 with 3, 0 with 1, 0 with 0. I can search for whole this 0, and then I can move to 2, and then I can say, okay, 2 with 4, 2 with 3. So I can make all the ordered pairs of using this kind of x values and y values, sometimes called the mesh grid. I can use that, and I can compute the value of z. Now for each pair, for each ordered pair in x and y, the value of z is basically the height that is basically leaving this plane of x, y. So consider this is x and y, that is a plane, and the height at a particular location, for example, at this particular x and y, the height is actually the value of the function, or the value of the z at this particular pair of x and y. The height may go in the other direction if the value of z is negative. So these kind of plots are three-dimensional plots, and they're very, very handy. And we are going to use this three examples of these three-dimensional plots here. One thing that you must notice here, that we will be using again matplotlib, plt.figure, and axis. When we generate axis, we will be primarily generating this figure.gca, the current figure, and we will talk about the projection 3D. There are other projection modes as well, but we will be talking about 3D. Let's make these wordings concrete in Python. Let me go to Python and actually code something for you. Just you can see this particular kind of plot that we've just seen in the slide. So let's, for example, import matplotlib. Maybe we just need to import some of matplotlib toolkits. So let's say toolkits.mplot3d, import that from this kind of toolkit mplot3d, import access 3d. So import that. I guess that's imported. Yeah. We already have NumPy, we already have PLT imported, so let's import this particular thing for 3D plotting. So let's have a figure, let's say plt.figure, let's have access ax as figure.gca. GCA is just the current figure, and we fix the projection type to be 3D. So that's our projection type 3D. So the environment for three-dimensional plot is basically set. That's the empty three-dimensional plot. If you see, I mean, nothing is there, but it's a three-dimensional layout that is set for you. So here you can have X label, you can have Y label, and you can have Z label. So let's, for example, set ax dot set X label, for example, X. And here now you'll be able to see this is the x-axis. Similarly, you can set the other labels as well. Maybe ax dot set y label as y, and maybe you can have ax dot set z label as z. So that's the empty plot that is available for you. Yeah, so that's the plot. Annotated with X, Y, and Z, and you can see here, I mean, the look and feel is really three-dimensional. I mean, all that stuff you're seeing here. So let's plot some data on top of that. Let's generate some data and plot on top of that. So let's generate some data. Let's generate, for example, let's say we have some value. Let's say we have some radii, just going into polar coordinates. Let's say we have some radius or r value. Let's say lin space. Maybe start from -2, go till 2, generate, let's say 100 points. And whatever you do, take a square of that, and then just add 1 to that. So that r will be a NumPy array with 100 values. In this particular format. Now next let's generate for example maybe x values. X is basically let's say x is simply r sine theta. So what is theta? Let's generate a theta as well. So some theta, that just to make a circular plot, let's generate a theta here. So theta is, let's say, np dot lin space, go from -4 pi to 4 pi for asterisk np dot pi, and generate 100 points. So that's theta. Let's say x is np dot sine theta, and y is, let's say, again r np dot cos theta, maybe. Yeah, So then z might be, for example, the same np dot len space like we did in r radius. Just let's say from -2 to 2, and let's say we have 100 of those points. So let's say that's our z. And next what we do is we say, okay, ax dot plot. We need not to set this as, already we have done this projection as 3-dimensional, so we need not to specify anything. We just call the function plot as it is, as we called earlier in 2-dimensional case. The projection 3D will handle the 3D plottings. We can set the label if we want. Label is let's say 3D, let's say 3D plot. That's our label. We can also have the legend. So let's say ax dot legend. So legend will be set automatically. Oh, what's the problem here? Oh, I have not entered the string here. So now if you see, you'll get a very cool plot here. This kind of plot, yeah. This is the plot. Yes. So that is kind of the plot. Here you have seen the this is the x-axis, this is the y-axis, this is the z-axis. I've just generated some parametric curve out of it, and that's basically a 3D plot. So the crux of the story is basically this projection 3D. Once you have this projection 3D available with you, the callings and all the rest of the story is just similar to what you are doing with 2-dimensional plots. Let me give a couple of more examples for these kind of for these plots. And further, by the way, we can use if I just use the layout, for example, if I'm right now I'm using the layout set by Seaborn. I can use a different layout, for example, plt dot style dot use, maybe I can use a different style, maybe classic, and then the things will look like different in a different way. So and you can have a lot of styles here. I mean, you can have a lot of styles. Let's check all the styles and just change the styles and see the look and feel. So plt dot style style dot available. So let's see. Oh, there are so many: dark background, fast, ggplot, Seaborn bright, Seaborn colorblind, and several of those. So many of them. So let's use, for example, this. Let's use this one. Let's use this one, and let's see how the plot looks like. Let's use this one. Just do. So now we have, we have a really different look and feel of, but just changing the style, we have this particular look and feel. Oh my God, that's awesome. Anyways, you can play with all these kind of styles and all the stuff if you want. I'm actually moving towards another example of a 3D plot in which we are going to actually use a 3D scatter plot. So by default, I'll be using the Seaborn layout. So let's do some plotting using the scatter plot. Again, I will be using figure as plt.figure. That's my figure. And we'll be using axis as figure.gca, whatever the current figure is, and the projection type is 3D. That's our projection type. So now what we really do is we have, let's say this x data is, let's say we have 100 points. Let's say we set 100 points. Let's say our x is simply is np.random.rand. How many of those? Let's say n of those. Let me, this is not rand n, this is not normal random distribution. This is the uniform random distribution. I'm generating n of n points. And let's have let's have this to start with, let's say 32, and end with, let's say, let's start with this in this particular range, just to set that this particular range, plus 23. So it will start from really 0 and go to 23. It basically that will so it will so basically I basically want to generate random numbers starting from 23 and ending at 32, and this basically will handle that, all that stuff for me. Next, let's say want to generate some other random data. Let's say another data, maybe and let's say right now we have like right now let's scale the data from 100 to everywhere, and np.random all these points, and let's say we have this as y, and let's generate a z as well, because we are going to do a 3-dimensional plotting. Let's do a z as well. So the z is for example, let's start it by maybe minus 25, for example, minus 25. So that's the upper limit, or plus, let's say this is 50, and asterisk np.random .rand n, and maybe now we add or we just subtract a 50 out of it, and these are this is our x, y, and z data. Next, what we do really is let's say plot ax dot scatter, and x, y, and z. That's our values. The color we are going to give that is let's say red. Well, let me just write this as C is red, and the marker we are going to use is basically let's say the marker right now is just that, and here you can see that's the scatter plot. We may be able to change the size as well. So size is, let's say so let's have a size also. So in this case we have a larger size, yeah. So that's the plot. We may be able to generate the data for example in another way, just to have another. Let's generate more data again randomly, and now let's use a different marker and different color just to see different kind of plots there. Let's use now blue color maybe, and let's use a triangle marker like this, and you'll be able to see two different kind of scatter plots in the same plot, like so. So that's what is happening. I mean, yeah, so that's completely a 3D scatter plot. Let me also introduce a surface plot for you in 3D, and then we will be primarily moving towards bouquet. Just let me give you one more example of this 3D plot, just a surface plot. We have seen a line plot, a curve plot, we have seen a scatter plot in 3D. Let me just use this surface plot as well. So let's say figure, let me make this a little bit higher. Let's say figure is plt.figure. That's my figure, let's say. And ax is again figure dot gca, the grunt handle, and the projection type is, let's say, 3D. That's the projection type. Remember in our one of our earlier calls, we have imported this axis 3D, yeah. So axis 3D. So we'll be using this axis 3D here as well, just to get some test data. There are some test data available in these axis 3D already, so let's use that. So let's get some test data using this axis 3D dot get get test data, test data, some data that is available. Let's set certain attributes, and if we just run that, we'll be having some test data that is available. Next, what we do is we say, okay, plot surface. That's a surface plot with X, Y, and Z as data. We can set our color map here. The color map is, let's say, cool, warm. Let's say that's our color map. And if we just run that, oh, it's nothing has shown. Why not? Access 3D has no attribute get test data. Why not? Maybe we have to import the Access 3D with, we have to import the Access 3D with smaller those. So let's from MPL toolkits dot mplot3d import Access 3D, Access 3D smaller, this one. So after importing that, let's use that AXES3D and get test data. Now it should work. It should work. It has worked. Oh my god, you see that surface plot here? Let me just, that's a surface plot. I mean, this is X, Y, and that is Z. That is completely a surface plot. We can set the alpha here if we want. Alpha equals, let's say, 0.5 just to see the opacity, and we can have this surface plot. We can have the surface plot completely in a different layout if we just change the style here. For example, plt.styles .use, maybe we use a different style and get maybe a different look and feel of the same plot. Just let's say we use the Seaborn deep style just to see what it does. Just use that one. And you might see everything. No, it doesn't change anything. In this particular case, it doesn't change anything. What if we use here, maybe, what if we use here BMH? What will it do if we use the BMH? Let's see. In this particular case, it is getting the same thing. I mean, that's somehow strange. Now you get a different kind of curve just by having this attribute different, by generating a different kind of data. You may have, for example, this alpha value a little higher to see less opaque this figure. I mean, that is a surface plot. How cool is that? You can set the alpha value to exactly 1 just to see the plot in more fancy colors. So that's it has generated some data, and XYZ is the data, and you just plot a surface, and that's the surface available to you. We can have more on this basically 3D visualizations, but right now I'm going to discuss basically a bouquet library that is very fancy and very handy to actually for browser kind of plottings and interactive plots. More 3D plottings, more Seaborn, more Matplotlib, more pandas, and all that stuff is basically available in detail, in full length, in our full-fledged course at AI Sciences. So do enroll that course if you really want more detailed treatment of all these subjects that you're seeing here.